In today's video, we are going to take what we did in the previous two videos and combine it so we can do what's known as curve sketching. The idea behind curve sketching is 3 steps. First, we analyze the function itself, f of x. We find the domain, we find any intercepts, we determine the end behavior, as well as determining any asymptotes. The second step is then to analyze the first derivative of the function, f prime of x. We look for intervals where the function is increasing and decreasing, as well as any relative extrema. The third step is we analyze the second derivative of the function, f double prime of x. We look for intervals of concavity, as well as any inflection points. The fourth and final step is to take all the information from the previous 3 steps and sketch the graph. For our first example, let's look at the function f of x equals 3x to the 4th minus 8x cubed plus 6x squared plus 1. And the first thing we want to do is we want to analyze f of x. First, we look for the domain. Well, this is a polynomial, so the domain is all real numbers. Now let's determine any intercepts. Y-intercept can be found by replacing x with 0. X-intercept is found by setting f of x equal to 0 and solving for x. Right now, we can factor out an x squared from the first terms. We get 3x squared minus 8x plus 6. That would equal negative 1. Now, since x squared is always positive, this would mean that 3x squared minus 8x plus 6 would have to be less than 0. Let's see if this is true. If we set it equal to 0 and solve, using quadratic, we'd have 8 plus or minus the square root of 64 minus 4 times 3 times 6, 72 all over 6, which is a contradiction. Or not necessarily a contradiction, but we can't have a negative under the square root, so there is no solution. If we take any number, plug in x equals 0, we find that 3x squared minus 8x plus 6 is always greater than 0. Therefore, this statement up here is a contradiction. And we get no solution. And so what we'll do is we'll say this is separate work here. So we only have a y-intercept at 0, 1. Now we want to determine end behavior. And end behavior is done by taking the limit as x approaches infinity and as x approaches negative infinity. Well, as x approaches infinity, our function will go to positive infinity. As x goes to minus infinity, our function again will go to positive infinity. Since it's a polynomial, there are no asymptotes. Next, we analyze f prime of x. All right, so f prime, we will get 12x squared minus 24, I'm sorry, that is not x squared, that is x cubed, minus 24x squared plus 12x. There's nowhere this is undefined. Set it equal to 0 and solve. Factor out of 12x. Left with x squared minus 2x plus 1 is equal to 0. This is now x minus 1 squared. So we get x is 0 or x is 1. We go minus infinity to 0, 0 to 1, 1 to infinity. This will wind up being minus, plus, plus. Again, plug in value from each interval to f prime and see if you get positive or negative. What this gives us then is increasing over 0 to 1, and again from 1 to infinity. Decreasing over minus infinity to 0. And we have a relative min. It's f of 0, which happens to be the y-intercept, which we found to be 1. Next up, we have to analyze f double prime of x. Right, so f double prime, 36x squared minus 48x plus 12. That's defined everywhere, so set it equal to 0 and solve. We can again factor out of 12. So divide everything by 12, we're going to get 3x squared minus 4x plus 1 is equal to 0. This can factor to x minus 1 times 3x minus 1. And so we have x is either a third or x is 1. We go minus infinity to a third to 1, 1 to infinity. And what we get is plus minus plus. This means we are concave up over minus infinity to a third, and then again 1 to infinity. We are concave down over a third to 1. And we have 2 inflection points. We have 1 at a third. We plug a third back in to the function, we get 38 over 27. And we have 1 at 1. Plug that back in, we'll get 2. Now we need to use all of this information. All right, so let's say here's our coordinate system. All right, start with intercepts. All right, we have an intercept at 0, 1. Let's say that's right about there. Next, use asymptotes. Well, we don't have any. Let's plot critical points. We have a critical point at 0, 1, which is already plotted. We have a critical point at 1, 2. Plot inflection points. We have one at 1/3, 38/27. Right, that'll probably be right about here. And then we have one at 1, 2, which is already plotted. Now let's use the rest of the information we have. We know that both ends will be going to infinity. From 0 to 1, we are decreasing. I'm sorry, increasing. So negative infinity to 0, we are decreasing, so that's going to be something like this. And remember, it has to cross the y-intercept. Increasing from 0 to 1 and 1 to infinity. Right, which means right at 1, it's going to be constant, and then it'll go back up. Now let's just make sure that this agrees with concavity. Concave up over negative infinity to 1/3, so that's up there, and then up again 1 to infinity. Concave down 1/3 to 1. So there's a rough sketch of our plot. Now for our second example. Let's look at the function f of x equals x squared over 1 minus x squared. Right, domain will be all real numbers except when 1 minus x squared is 0. So we'll have minus infinity to minus 1, minus 1 to 1, and 1 to infinity. Y-intercept will be 0. X-intercept, we have x squared is equal to 0, which means x is equal to 0, which is the exact same as the y-intercept. So we have only one intercept, and that's the origin. End behavior. Take a limit as x goes to infinity. That is going to be -1. Limit as x goes to negative infinity will also be -1. For asymptotes, we have two verticals. X is equal to -1, and x is equal to +1. We have a horizontal asymptote at y equals -1. If we analyze f prime now, f prime of x, this is going to be a quotient rule. If we simplify this, we'll be left with 2x over quantity of 1 minus x squared squared. Now, over the domain of f prime is completely defined. Right? So all you have to worry about is where it's equal to 0. So 2x is 0, which means x is equal to 0. go negative infinity to minus 1, then minus 1 to 0, then 0 to 1, and finally 1 to infinity. Analyzing this, we'll get negative, negative, positive, positive, meaning we are increasing over 0 to 1, unioned with 1 to infinity. We are decreasing over minus infinity to minus 1, unioned with minus 1 to 0. We have a relative min, which is f of 0. That's the y-intercept, so that's just 0. For the second derivative, once again, this is a quotient rule. And if we go and simplify this, this will leave us with 2 times 3x squared plus 1 over 1 minus x squared cubed. Once again, this is defined over the domain of f, so all we have to do is set it equal to 0, which means that 3x squared plus 1 is equal to 0, which cannot happen, and so we find no solution. This means we're going to have no inflection points, but we still have intervals to test, namely negative infinity to negative 1, negative 1 to 1, and 1 to infinity. And doing so, we'll get minus, plus, minus. So we are concave up over minus 1 to 1, and concave down over minus infinity to minus 1, and 1 to infinity. We can now sketch our graph. Again, start with the intercepts. That's 0. Next, plot any asymptotes. So we have 2 vertical asymptotes. We have one at negative 1. We have one at positive 1. And we have a horizontal asymptote at negative 1. We are concave down on the ends. And if we look, increasing, decreasing, we're also decreasing over the ends. So we can determine that the ends must be something like this. Then in the middle, it is strictly increasing. I'm sorry. It was increasing from 1 to infinity, decreasing from negative infinity to negative 1, but concave down. It's concave up in the middle, and it is starts off by decreasing and then turns increasing. This is a relative min, the origin. So it would do something like this. And that would be a sketch. For our next example, let's look at the function f of x equals x squared over x minus 1. Domain will be everything except 1. Y-intercept, we get 0. X-intercept, you should see we will once again get x is 0. So we only have, again, one intercept, and that is the origin. For end behavior, limit as x approaches infinity of f of x is infinity. Limit as x approaches negative infinity will be negative infinity. We do not have any horizontal asymptotes. We do have a vertical at x equals 1. We are going to have a slant asymptote, right? Remember from college algebra or pre-calculus, whichever one you took. A slant asymptote occurs when the rational function's numerator is 1 degree higher than its denominator. And to determine it, we just find the linear quotient. We don't care about the remainder, so our slant asymptote is y equals x minus 1. Sorry, this should have been a positive, so I want that to be plus. And this would be minus, and we'd be left with plus 1. If we take the derivative, it's going to be a quotient rule. And if we now simplify this, we get x squared minus 2x all over x minus 1 quantity squared. It's defined over the domain of f, so all we need to do is set f prime equal to 0, which gives us x squared minus 2x is 0, x times x minus 2 is 0. So x is 0, or x is 2. We'll go minus infinity to 0, 0 to 1, 1 to 2, and then finally 2 to infinity. And we will get plus, minus, minus, plus, so increasing over minus infinity to 0 and 2 to infinity, which are the ends, decreasing in the middle. So over 0 to 1 and 1 to 2. We have a max at f of 0. If we plug 0 back into f, we get 0, which is the intercept. We also have a relative min at f of 2. Plug that in, we get 4. Right, we now look at the second derivative. Once again, quotient rule. And if we simplify this, we'll be left with 2 over x minus 1 cubed. Again, no inflection points. And we still need to analyze negative infinity to 1. And then 1 to infinity. And we'll get minus plus. That means we are concave up over 1 to infinity. And we are concave down over negative infinity to 1 with no inflection point. Right. First, plot the intercept, which is at 0, 0. Plot the asymptotes. We have a vertical at 1. We have a slant at x minus 1. Or I'm sorry, x plus 1, right? Because I did change that. I don't know if I changed it here. X plus 1. And that'll do something like that. Then we'll have increasing to the max, and then decreasing. And then here, decreasing to increasing. With this being the relative min that I never plotted. One final example to look at. Let's consider the function f of x equals x minus 1 to the 2/3 power. Domain is the set of all real numbers. Y-intercept f of 0, we're left with -1. No, we're not. I'm sorry. We're left with +1. X-intercept f of x equals 0. This means that x minus 1 is 0, or x is 1. So we have 2 intercepts this time. We have one at 0, 1, and we have one at 1, 0. If we take a look, limit as x approaches infinity. This is infinity. And the same thing if we take a look at the limit as x approaches negative infinity. And there are no asymptotes. If we look at now f prime, we'll have two-thirds x minus 1 to the minus third, or 2 over 3 times x minus 1 to the third. Now if we look, f prime of 1 is undefined, and 1 happens to be in the domain. F prime of x can never be 0. So we only have a single critical number. We'll go negative infinity to 1, and then 1 to infinity. and we'll get minus plus. This means we are increasing over the interval 1 to infinity, decreasing over the interval negative infinity to 1, and we have a relative min at f of 1, which is 0. Now we look at f double prime. And this is a simple power rule. It'd be negative 2/9 x minus 1 to the minus 4/3, which is negative 2 over 9 times x minus 1 to the minus 4/3. Positive 4/3, I'm sorry. Again, this is never going to equal 0, but f double prime of 1 is undefined. Let me start that over. So we go minus infinity to 1, and then 1 to infinity. Here we will get minus, minus, so there's no inflection point. It is strictly concave down. All right, let's now sketch out two intercepts. We have 0, 1, and then 1, 0. And we know that the tangent line at 1 does not exist. We know it goes decreasing and then increasing, and it's strictly concave down with no asymptotes, so it's going to look a little something like this. If I draw it from this intercept, go that way, and then like that. And that concludes this video on curve sketching. In the next video, we will look at exponential growth and decay functions. So I will see you all in the next one.